Well, I'm very happy to, present this talk about extraterrestrial life in the solar system. And it sounds a little funny because when we use the term extraterrestrial life, we probably think about life on other worlds far away, other solar systems, other planets orbiting other stars. I'll be talking about at least the possibilities of life on other worlds within the solar system, and in particular, some of Jupiter's moons that are particularly interesting from this regard. And I'll explain why. So, um, the what's a search strategy for extraterrestrial life? And I'm talking not about animals or extraterrestrial animals or plants. I'm talking about simple things. Let's think about single-celled organisms, for example, or bacteria. Um, Nevertheless, life that formed on other worlds in the solar system, completely independent of Earth. So, the search strategy that NASA has used is basically follow the water. Look for worlds in the solar system where there was or is liquid water that has existed for a long time, because we know on the Earth that life on the Earth started in the oceans. We have the fossil record on the Earth that goes back 3.9 billion years, not terribly different from 4.6 billion years when the solar system itself was formed. So quickly after the Earth cooled in the formation of the solar system, life developed in the Earth's oceans. Are there other places in the solar system where that might have happened? And the answer is yes. And one of the worlds, for example, is the planet Mars. And there have been a lot of NASA missions to Mars. More are still being planned. How do we know that? How do we know that we should follow the water? How do we know that there was water on Mars in the past? Well, I mean, we see photographic evidence of it, and this is an image taken by a spacecraft orbiting the planet Mars, and this is an impact crater. In other words, a place where a chunk of rock smashed into the surface and dug out a crater on the Martian surface, and there's water ice. We can identify that as water ice. So it's not liquid water, but nevertheless, it is water in its frozen state. And perhaps if Mars was warmer in the past, this would have actually been liquid. Or this image, which I think goes back a long ways. This could have been one of the original Mariner 9 images that was photographed when the first spacecraft went into orbit around the planet Mars. And this is back in the 1970s. But look, I mean, there are impact craters that makes it, that shows that we're not looking at the planet Earth. But look at this sort of series of channels that have been carved in the surface. And we know we know what caused that. I mean, we look at it and it's very much like the reminiscent of for example, the Nile Delta regions on the Earth. These were cut by flowing water, a lot of it. So there are huge floods on the surface of Mars in the past. A lot of liquid water existed on Mars in the past. Or this more recent photo from a more recent modern orbiting spacecraft. And look, we're looking at basically a kind of a Martian floodplain. We can even tell which way the flood waters came. Look here and look here at these deposits. It moved from massive amounts of water, moved from the left to the right and form these structures, these channels that we see over here. Yeah, there are impact craters. So we're definitely looking at the planet Mars, not, for example, the planet Earth. But the geography of the terrain, is very, very similar to what we see in some areas on the Earth, caused again by flowing water. And if we can go down to the small scale, now we're looking at things that are only a centimeter, a fraction of an inch across. but there are rocks on the surface of the Earth and on the planet Mars that are exceedingly similar in form. And on the Earth, we know that these rocks, this gravel, was formed in flowing water, in a river, in a stream, and these same kind of rocks exist on the surface of Mars. And that is certainly proof that there were streams on the planet Mars, rivers on the planet Mars in the past. Now, this could have been, admittedly, a long time ago. The conditions on Mars are such now, today, that we can't have liquid water existing on the surface for very long because Mars is much too cold, the atmosphere is much too thin to allow liquid water to exist for very long on the Martian surface. But it did exist for a long time in the Martian past, enough to form these rivers and form these rocks. So what are we talking about? If we could, in imagination, and this is speculation too, of course, look back or imagine the past on Mars. Mars must have been a very different world. Maybe 3 billion years ago, Mars was certainly a much warmer world, a much wetter world with liquid water on the surface. So we see in this artist's conception, admittedly, an atmosphere with clouds, water oceans on part of the surface. Mars very, very probably looks something like this in the early history of the solar system. It doesn't look like that today, but it did in the early solar system. So follow the water, follow the water. If we see evidence for water, either at present or in the past, that's the place to look for life. So we are looking now at the so-called Galilean satellites of Jupiter. They're called the Galilean satellites. Galileo discovered these satellites, these moons of Jupiter, in the year 1610 with his homemade telescope, which was probably optically not as good as a decent pair of binoculars that you can buy not terribly expensively here on the Earth today. And yeah, with a pair of binoculars, if you look at the planet Jupiter, you can see the Galilean satellites. You can see these 4 large satellites of the planet Jupiter. Now, again, Jupiter, this is not a Galilean satellite over here. This is the planet Earth. But you can sort of see in comparison, size comparison, Jupiter is a huge world. It's not like the Earth. It doesn't have liquid water. It doesn't even have a solid surface, just a very, very thick atmosphere made up mostly of hydrogen and helium. But here's the Great Red Spot, which you may have heard of, a gigantic cyclonic flow in the atmosphere, a hurricane, basically, in the atmosphere of the planet Jupiter that's been around for more than 300 years. But it's a huge world. The planet Jupiter is more massive than all of the other planets in the solar system put together. Huge amount of gravity there, and we'll talk more about that, the influence that it has. And here are the Galilean worlds. Now, this is the planet Jupiter again, and here's the Great Red Spot. And here are the 4 Galilean satellites. Now, they're sort of posed together in this picture. They're not as close as that. They're not as close as that to Jupiter, and they're not as close to themselves either. But one thing that you should see posed for this photograph are the 4 very, very different worlds, and they look very different. This is the satellite, the moon Io, the moon Europa, the moon Ganymede, and the moon Callisto. And we can sort of make a kind of a rogues gallery of them here. And the important thing that I draw out to you is that these worlds look very, very different, and all 4 of them are unique. We'll see that their appearance and their composition and their activity is strongly driven by how close they are to the large and massive planet Jupiter, which has a great influence on what they're like and what their interiors are like. And these are large moons. These are moons that are appreciable in size. They're most of them larger than the Earth's moon, and the satellite, the moon Ganymede, is actually larger than our planet Mercury. So if in imagination we could take Ganymede and put it into orbit around the sun, we would have to call it a legitimate planet. It orbits Jupiter, so it's not classified as a planet. It's a moon, a satellite of the planet Jupiter. But these are large worlds. These are unique worlds. Let's find out a little bit more about them. Well, there are three icy moons of Jupiter. Those are Europa, Ganymede, and Callisto. I have to mention, at least briefly, the non-icy moon, which is Io. Io is strange, and this is a world. Here's a photograph of it by a spacecraft, not in orbit around the moon, but in a flyby mission. And gee, that looks funny. It looks odd. The colors are odd. These features on the surface, they're odd too. One of the things that we don't see that are very common in the solar system are the Earth's moon, like the Earth's moon, are impact craters. And I talked about that in the case of the planet Mars. There are impact craters on the planet Mars, lots of impact craters on the Earth's moon. Relatively few impact craters on the Earth, but that doesn't mean that the Earth wasn't hit by chunks of rock. It means that erosion, water erosion, wind erosion, crustal plate motion has all basically resurfaced the Earth's surface and actually redone the surface and covered up, obliterated most of the meteor craters on the Earth. But not here on Europa. There don't seem to be any impact craters at all. What's going on? Turns out we're looking at a volcanically active world, and it's far more volcanically active than the Earth. There's no water on the surface. There's no water in the interior. This volcanic activity is driven by the huge gravitational force of the planet Jupiter, which kind of squeezes and flexes Io because it's so close to the planet Jupiter in its orbit, and actually melts the interior and drives this volcanic activity. What we're seeing over here is another shot from a different angle, but what we're seeing here is an actual volcanic plume on the surface. So there are immense amounts of volcanic activity. At any moment, there are literally hundreds of volcanoes or volcanic vents on the surface of Io. 10% of them are actively erupting at any time. So this is a remarkable world, but as a candidate for life, follow the water. Well, there really isn't any water, so there's nothing to follow. And the two spacecraft missions that I talk about will not be thoroughly exploring it. Here's an image of the satellite Io in the infrared, showing heat on the surface. And all of these bright spots are volcanic vents, higher temperatures and material that's erupting out onto the surface of the moon Io. So that's not where to look if we're following the water, but a very, very interesting and important moon to look at if we're following the water is the second moon out, the satellite, the Galilean satellite Europa. A very, very interesting world. And if we look at it, it looks funny too. It's a very, very smooth surface. It's not, a lot of volcanic vents and plumes like Io. It has very few impact craters on its surface, but we see cracks and lines and grooves on the surface. So what are we looking at? Let's sort of see if we can zoom in a bit and take a look at this image of Europa. That might be an impact crater over there. But how many impact craters can I see? That might be an impact crater there, just a couple. And then there are all these very, very smooth surface with a lot of cracks in it, with a lot of grooves in it. So what are we looking at? Oops. What are we looking at? Well, here's a close-up of the surface. This was actually done, an image that was taken within the past year. There is a NASA mission that's orbiting Jupiter right now and has been for at least the last half dozen years. That's called Juno. And the Juno spacecraft has been in orbit around the planet Jupiter, spending much of its time photographing and mapping and measuring things on the planet itself. But recently, they've been retargeting, changing the orbit of Juno to do some close flybys of some of the Galilean satellites. And this is what it looks like, a very cracked and complex looking surface, maybe an impact crater here or there. Not very much though. And then what are we looking at? What kind of a surface are we looking at? Well, here's an older image. This could date back to the Voyager spacecraft that flew by the planet and its moons in the early 1980s. And what we're looking at is really an ice surface with a lot of cracks in the surface. And when we look at a section of the surface like this, it really is reminiscent of Arctic or Antarctic regions on the Earth, where we're looking at, for example, ice flows. And this pattern that we see, cracks in the crust, sort of these irregular features that almost look like diamond shapes. These could be ice flows. That is icebergs, if you will, ice flows that are sort of floating above a water surface. And there is a very good evidence, very strong evidence for the existence of a subsurface liquid water ocean on the satellite Europa. Maybe I should say in the satellite Europa. An ice surface, but underneath the ice surface, a liquid water ocean. So exciting stuff. Follow the water. Follow the water. And here's Ganymede, the third Galilean satellite. Again, doesn't look like Io, doesn't really look like Europa either, because we do see evidence of impact craters, actually a number of them, but there's clearly other darker areas and regions where something's happened. Let's take a closer look at this and sort of see what we're seeing here. Now, here's an impact crater. Yeah, so there's a bunch of impact craters, more than we see on the Earth, a lot fewer than we see on the Earth's moon, for example. But look over here. There are also these parallel grooves and cracks that we can see all over the surface. And, that's kind of reminiscent of what we're seeing on Europa. So what we think is, once again, we think what we've got is an ice-covered world with possibly a liquid water ocean underneath. So here's a more recent image from the Juno spacecraft, I believe, again, maybe about a year old or so. And these are the whitish areas that we see are impacts on the surface, but they might have exposed fresh ice underneath it. So there's an ice surface, definitely an ice surface on the satellite Ganymede. And then here, a little, impact craters. Yeah, sure, impact craters, but we're not so much interested in that. We see that on many, many other worlds in the solar system. But look at these cracks and grooves in the surface, a lot of them. And again, indicative of the fact that there is an ice crust, an ice layer that has kind of broken apart due to internal motions. And these internal motions, similar not exactly the same, but similar to crustal plate motion on the Earth, have actually cracked the ice surface of Ganymede. And where does the energy come from for these internal motions? Answer: the gravity of the planet Jupiter. That's flexing the interior of this moon to a lesser extent, though, than um, than Io, of course. And the last Galilean is Callisto. Again, here's the Earth, here's the moon. Callisto is a large moon. It's not the largest moon. The largest moon is Ganymede, but still, this is considerably larger than the Earth's moon, smaller than the Earth itself, of course. But what do we see? Well, Callisto is peppered with impact craters. But again, the impact craters don't look like the same as impact craters on the Earth's moon, for example. Rather, they have these whitish centers, at least many of them do. And it looks like we're looking again at an ice surface with fresh ice being excavated by a relatively recent impact. So what we're looking at is an ice-covered surface, relatively recent impacts, and this one is a feature on the surface of Callisto called Valhalla, and it is a big impact. And actually what's happened, look at these concentric circles around it. The impact produced shock waves, which, sort of shattered the crust and made these concentric circles. We don't see the lines and grooves on Callisto that we see on Europa or Ganymede. So the surface appears to be, the interior and the surface seem to be less active. There may be a water ocean underneath a thick ice layer, but it's harder to prove than in the case of Ganymede or Europa. So many impact craters. It looks like relatively speaking, like a geologically dead world. I've talked about this. In fact, I remember I said that I expected before the New Horizons flyby of the planet Pluto a few years back, I really expected the surface of Pluto to look like this. Kind of relatively uninteresting, lots of impact craters, but nothing really happening on the surface or in the interior of the world. Well, certainly in the case of Pluto, that turned out not to be the case at all. Pluto is dramatically different than what I expected, certainly. So the two moons to really look at closely are Europa and Ganymede. So why are we talking about the icy moons, Europa, Ganymede, Callisto, as possibilities for life? And again, let's remember that we're not thinking about sort of complex life, advanced life. We're not talking about plants or animals, but perhaps the possibilities of single-celled organisms similar to bacteria or plankton on the Earth, things that are that were at the start of evolution on the Earth. So why do we think that's the case? Well, if we theorize about the internal structure of Ganymede and Callisto and Europa, we have good evidence, and in some cases very strong evidence, for the existence of liquid water oceans. So let's look carefully at this. I mean, there's a surface here, which is an ice surface, and we see that for all three worlds. But then below the ice surface, it really does look at the blue on all of these. It really does look like we have oceans underneath, liquid water oceans underneath the surfaces of these icy worlds. So surface is ice, water ice, but below the surface. Now, how thick is the ice layer? Good question. It could be not as thin as we have in the Arctic regions of the Earth, but it could be relatively thin, maybe a few kilometers, a few miles in thickness. But then below that, there would be liquid water oceans. And we're not talking about a little bit of water. I know, yeah, these satellites are all smaller than the Earth, but these oceans are modeled and predicted to be very, very deep, a lot of water. Europa, for example, is estimated to have twice as much ocean volume as the Earth. So there's a lot of water, and if we're using the NASA model, follow the water, boy, all three worlds have very, very reasonable possibilities for life. We should certainly look at them very carefully, and in particular, Europa and Ganymede. And in fact, here's an artist's conception of a possible model for the upper layers of Europa. On ice crust, there are these vents here, not volcanoes, but just geysers, I guess would be a better word for it. We'll talk more about these in a bit. And here's a crack in the ice layer that allows water and icy compounds, I guess, to be released at the surface. And then below that big blue thing, that is the subsurface ocean. And a very deep ocean it is, hundreds of kilometers thick, compared to a few kilometers thick on the Earth's oceans. So, if Europa in particular is so interesting, and the NASA mission to Europa is going there, it's called the Europa Clipper, and we'll talk about that in a moment. Why not just go into orbit around Europa and spend a long time mapping it and looking for, evidence of the geysers and the vents, and what are the geysers made of? What's the material that they're venting? And would be easier to do that from orbit. The information that we've got about the planet Mars, for example, really exploded when we put spacecraft into orbit, and of course then landed on Mars, on the Martian surface too. There were flybys of the planet Mars before there were orbiters, and the flybys showed a little bit, but not to any extent the degree of information that we've gotten from orbiters. So why not put a spacecraft into orbit around the planet Jupiter? Well, that's very hard, and here's the reason. The Earth has a magnetic field. We know that compass needles point north. Here is the Earth, and here's a compass needle depiction here. And these are the magnetic field lines. We know about this. We're familiar with this. We probably heard about this in science class. We might not know about this because the magnetic field is not harmful, but what it produces is, and let's blow this up, there are particles that the sun emits. I mean, the sun emits light, visible light, but it also emits particles. Most of those particles, subatomic particles, are protons and electrons by a process called the solar wind. And the solar wind interacts with the Earth's magnetic field. And some of the particles in the solar wind are actually trapped into what are called the Van Allen belts, named after James Van Allen, who was a physicist at the University of Iowa, I believe, and discovered them. They were discovered shortly after the first satellites were launched, when these were detected. But these are high energy particles that have been trapped. They come from the solar wind. They've been trapped by the magnetic field of the Earth. Now, their prolonged exposure to these high energy particles for people would be dangerous. So astronauts can travel through the Van Allen belts if they're going to the moon, for example, um, and that's okay because they cross through the Van Allen belt, spend very little time in the areas where the high energy particles are. But you wouldn't want astronauts to orbit within the Van Allen belts for an extensive period because that would be dangerous. Uh, and it would also be dangerous not just to the bodies of the astronauts, it would also be dangerous to the electronics on board the spacecraft, on board the satellite, or on board the rocket that you're using to get from here to there. So high energy particles are not kind to people, and they're not kind to electronics on board spacecraft either. So, got to be careful about that. And here's why Europa is problematic. Now, Jupiter has an immensely powerful magnetic field, many times stronger than the Earth. And let's see if I can find yeah, here we go. Um, so we're looking now at a model, an artist depiction of the magnetic field around the planet Jupiter. And this produces, they call it plasma torus, but it's actually a gigantic Van Allen belt. So the particles from the solar wind are being trapped by Jupiter's immensely strong magnetic field. By the way, some of the particles in this so-called plasma torus are actually from Europa, and they say from Io, and Io delivers a ton per second of, of stuff that comes out of the volcanic events, which are mostly sulfur and compounds of sulfur. They have sulfur dioxide, SO2. So Europa orbits right within the Van Allen belt, and that if we try to imagine a spacecraft mission from Earth going into orbit around Europa, it would not last very long because of the very very high radiation levels. Ditto for Europa. Okay, it's farther away from Jupiter, and that means that it's orbiting at the edge of the Van Allen belts of Jupiter, but still enough radiation coming down onto the surface of Europa and the vicinity of Europa to be dangerous. And these are not the missions that I'll be talking about are not manned missions to Europa or Ganymede, but the electronics of spacecraft would be they would be fried if you tried to orbit Europa. Ganymede is outside the Van Allen belts for the most part, and Callisto is very far away from the Van Allen belt. So these are safe, but if we want to explore Europa, we can't orbit it. But we have other ways of doing it. So a Europa orbit within this high radiation environment is just unthinkable. It wouldn't work. The spacecraft wouldn't last very long at all. Okay, so the NASA mission to Europa is called Europa Clipper, and it's a bunch of flyby missions. Here's the spacecraft. It's not yet finished. It hasn't been launched yet, and it is being assembled at, I assume, Jet Propulsion Labs out in California. And this is a clean room. Here are people over there, and you can sort of see it's, maybe 2 or 3 times the height of a person, but it is not yet finished. It's still being constructed in this clean room to keep it absolutely dust free, so that nothing could cause the electronics or the optics in the spacecraft to malfunction. Recently, within the past few months, I think, the antenna in this photograph, it's not here, but the antenna, which is this circular thing here, has been added. The high gain antenna is actually the way that the spacecraft communicates to the Earth. It sends data back to the Earth from the missions. It receives data from the Earth commands that would modify the mission parameters. but the high gain antenna has recently been put on, and we're in the same clean room. Here's still people down over here and there, so you can compare the size. I think that on one of the sites I read that it's about the size. This craft and the other mission, JUICE, the mission from the European Space Agency, they're about the size of a garden shed, I think they said. Now, you don't see it here because they haven't been attached yet. They're big solar panels that are attached to Europa Clipper and to JUICE, the European Space Agency mission. You need big solar panels to power the spacecraft, to power the electronics, and also to keep the spacecraft warm. It's really cold out there. It's very far from the sun, many times the distance of the Earth from the sun. Solar panels will work, but they'll be much less efficient, so you need a large area. This, by the way, is a basketball court down here. So you can sort of see that these solar panels are big, but these lines here are hinges so that they're folded up inside the launch vehicle, and then once the spacecraft is outside the Earth's atmosphere, they unfold and begin to work, gathering solar power, converting it to electricity. And then, last but certainly not least, it's always nice to have artists' impressions of, here's Jupiter, this is Europa, note the cracks in the smooth surface, and here is Europa Clipper in orbit with the solar panels extended. So what's the mission like? Again, you can't orbit Europa. It's within that radiation belt, and it hasn't been launched yet. The launch is scheduled for October 2024. There will be gravity assists. That means that the spacecraft will pass very close to the Earth and Mars and basically be boosted, flung off by the Earth's gravitational field. They'll pick up momentum, and it'll get to Jupiter faster. There'll be a flyby of Mars, there'll be a flyby of the Earth, and it will arrive in the vicinity of the planet Jupiter. It will orbit Jupiter, again, not Europa, but it will orbit Jupiter in April 2030 if all goes according to plan. Again, taking nearly 6 years to get there. But the solar system is a very big place. The outer planets, Jupiter, Saturn, Uranus, Neptune, all of these are very far away. Takes a while to get there. So the plan is that it'll be a Jupiter orbit. There will be 44 flybys of Europa that will be made by Europa Clipper. Not orbits, but flybys. But the altitudes will range from 2,700 to 25 kilometers. Now, 25 kilometers is about maybe 15 miles, between 15 and 20 miles. That is incredibly close to the surface. And one of the things that will be done is that there will be a complete mapping at very, very high resolution, very, very exquisite detail of the surface of Europa by Europa Clipper. So it'll map the surface. There are instruments on board to attempt to measure the ice thickness and sample those ice plumes, basically to see what they're made of. Liquid water, we believe, but anything else, any other compounds that are present in the ice plumes that could, again, provide hints for the possibility of life in the deep liquid water oceans. And there are ice plumes. I mean, I had an artist's conception that I showed you, and it wasn't speculation because the Hubble Space Telescope has actually observed these ice plumes. Here's 2014 and here's 2016, and these are extending, dozens or hundreds of kilometers above the surface. So there is ice, there are liquids that are exiting through cracks in the surface and then being expelled out into space. It would be very nice to fly through one of these ice plumes and sample the contents. Here is a little bit more detail, and let me sort of expand that and show you. So here's what the flybys look like. Here's the planet Jupiter. Here's the orbit of Europa. And again, this is an elliptical path indicating the orbit of Europa Clipper. So it goes close, it goes into the radiation belts, but doesn't spend much time there. So, and then it goes out and it's safely beyond the radiation belts over here, where it spends most of its time in its orbit. And they're changing the orbit. They've got fuel on board, thrusters on board, so that they'll gradually change the orbit to be able to change the approach toward Europa and basically be able to map the whole surface. By the way, this is a map of the dose rate in rads per second, and it's very, if it's red, it's very high dosage, and then if it's down to purple and even green, it's much lower dosage. So the instrumentation on board Europa Clipper is shielded from radiation, but the higher the dose rate, the less effective the shielding is. So we still can't orbit Europa even with shielding. So the second mission is called JUICE, and it's an acronym, Jupiter Icy Moons Explorer. And this is a mission by the European Space Agency, which is on its way. The JUICE mission was launched in last April 2023. And, here it is. Here's what it looks like. Let's kind of sort of blow that up, yeah. And here is here's a high gain antenna. We can recognize that. All spacecraft need that to communicate with the Earth. It was launched from a launch pad in French Guiana in South America. French Guiana, that launch pad and the launch vehicle that was used is actually the same launch vehicle and the same launch location that was used to put the James Webb Space Telescope into orbit around the sun. So I think up here, this is ready to go now. Here are the technicians. They're in a clean room in French Guiana, and there's a kind of a stack. This is a stack of solar panels, because once again, we need a lot of solar panels to generate electricity for the spacecraft. And we'll talk about that in just a moment. And here's something very cool. This is a protective cover that they put on the spacecraft right before launch. And I got to show you, got to show you what it looks like. And there it is, a friendly planet Jupiter smiling, I think. And then here are the four Galilean satellites. And here, this one, I think, is the welcoming arms of the Galilean satellite Ganymede, which the mission JUICE will eventually orbit. And then down over here are signatures of a lot of people that helped to put the spacecraft together. Now, this was not launched into space. This was a protective cover. So as far as I know, it didn't get into space. But anyway, I think it's cool. I wish NASA did stuff like that. Maybe they do. But here's the launch, which took place on April the 14th, 2023. There it goes. And again, the booster is an Ariane 5. Same booster that launched the James Webb Space Telescope into its solar orbit, and a very, very reliable launch vehicle, and it was reliable for the launch of JUICE. And let's see, here is the spacecraft in orbit. Well, no, ours conception, and it's actually in orbit around this particular thing. What is it orbiting? It's actually orbiting Ganymede. We'll talk about that in a bit, but here we go. Big solar panels. Need that because it says solar panels are 800 million kilometers from the sun, And, the Earth is only 150 million kilometers from the sun. So you need them to be big to generate enough electricity. They've got a radiation shield. Yes, 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 we need that. Here's the planet Jupiter farther away. Blanket for minus, well, a sort of insulation from the very, very low temperatures of outer space. But there we go. So it's on its way. The focus of the JUICE mission is going to be on the satellite Ganymede. Launch 2023 will not arrive at Jupiter till after Europa Clipper, July 2031. I believe that, it was launched earlier, but it arrives later. What's going on? It is a more massive spacecraft than Europa Clipper. So it needs, it gets gravitational boosts, but the higher the mass of the spacecraft, the less effective those boosts are. So it needs more time to get to the region of the planet Jupiter. And in fact, it does 4 flybys for gravity assist. It flies by the Earth, then it flies by Venus, then it flies by the Earth, then it flies by the Earth again. So it's taking a very circuitous route to get to Jupiter and eventually orbit Ganymede. It'll go into orbit around Jupiter in July 2031. So it will first orbit Jupiter, and then there'll be flybys. They're going to be flybys of Europa, not very many, I think only a couple. There'll be flybys of Ganymede, and there'll be flybys of Callisto. Europa Clipper will pay no attention to Callisto whatsoever, I don't think. But so there'll be flybys of all 3 of the icy moons. And then in December 2034, the spacecraft will go into orbit around the satellite Ganymede. And it will be a circular orbit, about 500 kilometers altitude, in a very, very superb position to photograph and measure things on the entire world of Ganymede. And this will actually be the first spacecraft in history to orbit a planetary moon. In other words, not the moon of the Earth, some other world. Orbiting Mars doesn't count because that's a planet, but planetary moons. So the first spacecraft to ever do that. Best of luck. And then I want to talk about there'll be cameras, there'll be instruments to measure the magnetic fields, measure the radiation environments. Here it is in orbit around the planet Jupiter, and there's the high gain antenna, solar panels and stuff. But one particularly interesting instrument to me is an instrument called RIME, R-A-M-E, and that's an acronym for Radar for Icy Moons Exploration. And RIME is it's a radar unit that will actually it's a penetration radar. You've perhaps heard on the Earth of using ground penetration radar. It's done sometimes on the surface of the Earth. This is study the subsurface ice on these worlds to a depth of at least 9 kilometers. Sounds like incredible fun. And I hope that they'll be able to do this for Europa and for Ganymede and for Callisto, certainly for Ganymede. But terrific mission, ambitious, more ambitious in a way than Europa Clipper because it's doing more. And how long will it remain in orbit around Ganymede? Well, we don't know exactly until it runs out of fuel to make orbital corrections. And then the plan is to actually crash it into the surface of Ganymede. But the one you may have heard about this, there was news reports about this. This is actually a kind of a selfie of the JUICE mission looking back toward the Earth right after launch. So here's JUICE, and there's the Earth. So this is literally a few minutes, half an hour, something like that, after the launch of the spacecraft. And right over here, a little hard to make out, admittedly, is the antenna for RIME. And the antenna is not a dish antenna, just a big, long rod, um, sort of articulated and so that it would collapse into a small volume. But then, of course, they had to extend it out, and it stuck. It got stuck. So this is the folded up rime antenna. The antenna was stuck. It wasn't, they tried to deploy it, didn't quite work. Well, then they tried other things. They shook the spacecraft. They turned the spacecraft so that they might have said, well, maybe it got frozen. Maybe if we put sunlight on it by rotating the spacecraft, we can warm it up. Eventually, it did deploy, and I think that the RIME antenna is this. It's very long. It's about 50 meters in length. And that so the ice penetrating radar should be up and running, and a good thing too. Um, we're about at an end here, but one thing I want to talk about, make sure that we're clear on this. Both of these missions, Europa Clipper and JUICE, are not designed to find life on any of the Galilean satellites. That's not the purpose. But Europa, Ganymede, Callisto, all of these are very, very intriguing worlds. And if we're doing a follow the water kind of expeditions to these worlds, we really need to find out more about them. We've had very, very limited flybys of all three worlds, Europa, Ganymede, Callisto, and we need to find out a lot more about them. And then maybe the next missions after this will be the missions to actually explore for life. Who knows? There might be landers on Europa or Ganymede that could land on the surface, robot landers, and explore and find out even more. But it all depends on what we learn from both Europa Clipper and for JUICE. I think these are incredibly exciting missions. It's too bad we've got such a long wait, 6 years, 7 years, 8 years even, to see what happens. But I think that these will be wonderful missions. We'll learn a great deal about all of these worlds. Thank you very much. I appreciate your listening to this.
Thank you, Bernie. I know all the people in EAS really, really, really appreciate these talks that you do for us, and especially that you record them for us.
Happy to do that. Happy to do the talks. Happy to make recordings. I'm so glad that we began to do this. Maybe not many good things came from COVID, but perhaps this is one small example of something good that came from the result of that terrible epidemic.